Dear colleagues, nice to meet you. I represent paper 101, topic case-driven TLC model checker analysis in energy scenario. Our group of authors represent four institutions: National University of Life and the Environmental Sciences of Ukraine, G. Pukhov Institute for Modeling in Energy Engineering of the NES of Ukraine, Institute of Electrodynamics of the NES of Ukraine, University Technical Malaysia Melaka. Problem statement. Paper addresses the problem of an exponential growth of the transition system state space in terms of corresponding computational and spatial expenses. Named problem has been examined in terms of the TLC model checker implementation. Two alternative implementations of the TLC have been investigated in terms of the related computational and spatial expenses. The BFS breadth-first search one implemented by the default and the alternative DFS depth-first search implementation. The idea is to estimate and compare different implementations of the TLC method by ground in a particular case-driven scenario with respect to corresponding computational and spatial expenses that take place during the model checking. This approach is an attempt to discover and assess the factors, e.g. the architecture, structure and complex, specified in the formal model, number of state variables, etc., affecting the computational and spatial costs of formal application with a particular implementation of certain model checking, the TLC in our case. Moreover, an attempt to estimate the outcome of bringing the multi-threading to the implementations of the TLC method has also been made. Literature review. Nowadays, at the complexity level of modern program algorithmic solutions addressing the scenarios taking place in diverse safety-critical domains, e.g. energy scenarios, Finnish nuclear instance, for instance, avionics, satellite operational mode management scenarios, safety-critical system software as a part of railway control systems, etc., typically exceeds the limitations of computational and spatial resources required to successfully apply time-proven formal verification techniques and corresponding instruments in one-to-one manner due to exponential growth of transition system state space to be traversed through during an automated formal verification by way of model checking. For instance, considering the avionics scenarios, an exponential growth of both spatial and computational expenses has been faced in our previous works. Possible solution: vary the atomicity level to be applied in formal specification by coupling the specified properties into the groups, i.e. the hyperproperties. To this end, the broadly applied temporal logic of actions by Leslie Lambert and the corresponding TLC model checker have been brought to the use. Alternatively, the decomposition-based approach can be applied. Formal specification is decomposed into sub-specifications to be subsequently verified with the time-proven even B method. Literature review. Yet another promising direction is to decrease the model checking related computational expenses via mu calculus based abstraction reduction technique implementation. In addition, the bounded model checking approach can be applied. Moreover, the reduced ordered binary decision diagrams are shown to be the proven instrument. To formally check the abstractions applied in specification, deductive verification based technique can be utilized prior to the model checking. To address trade-off between the exhaustive nature of model checking facing the exponential growth of transition system, state space and case-driven testing, an attempt to construct the bridge between the model checking being applied at the design stage of engineering process and the validation by way of testing has been made with the MET model checking driven explorative testing framework. Moreover, the compositional model checking techniques can be applied e.g. the interaction preserving abstraction IPA framework addressing the specifications written in TLA+. Materials and methods. In given paper, the model checking task has been resolved with respect to a case-driven scenario taking place in energy domain and specified with a role model of European Identification Codes Registry update process. This problem is of the topical ones, taking into consideration current situation in Ukraine and the necessity to get coupled with the European energy market. The idea is to estimate and compare different implementations of the TLC method by grounding on a particular case-driven scenario with respect to corresponding computational and spatial expenses that take place during the model checking. This approach is an attempt to discover and assess the factors, e.g. the architecture, structure and complex, specified in the formal model, number of states, variables, etc., affecting the computational and spatial costs of formal verification with a particular implementation of certain model checking. the TLC in our case. Moreover, an attempt to estimate the outcome of bringing the multi-threading to the implementations of the TLC method has also been made. At the demonstrative problem domain, where diverse safety-critical scenarios take place, modern electricity market of Ukraine, adjusted in accordance with the harmonized European electricity market model, has been considered. European Identification Codes Registry Update process has been addressed as a case study depicted in the figure 1. Materials and methods. Considering the UML diagram depicted in the figure 1, the TLA plus specification at atomicity level has been chosen to be applied in one-to-one manner. In the figure 1, a fragment of the complete role model is depicted as the UML activity diagram. A complete role model encompasses 23 activities plus 6 conditional operators. Named model is approached as an artifact, an entity with the architecture, structure and complex, and the content. These constituents are represented in the formal TLA plus specification with respect to approach described below. Materials and methods. To synthesize the formal specification suitable for verification in an automated manner, the following two-stage approach has been applied. To create the architectural prototype encompassing both algorithmic structure and the couplings in a pseudocode-like manner of yet to be synthesized TLA plus specification. The plus Scala algorithmic language has been used. An outcome of this stage is an input data for the following one. The plus Scala specification has been treated as a preliminary artifact. It has taken 348 rows of pseudocode to represent the role model depicted in figure 1 in plus Scala. To generate the resulting artifact, the TLA plus specification from the plus Scala pseudocode that the TLA Plus Toolbox IDE integrated development environment has been utilized. The TLA Plus specification has been addressed to be the input data for the TLC model checker and to be applied in an automated manner. Named specification for figure 1 has been synthesized containing 508 rows of code. Experiments and results. Experimentation has been conducted on the platform, which is depicted in the 8th slide. During these two alternative implementations of the TLC model checker have been encompassed the BFS breadth-first search and the DFS depth-first search based ones. The obtained results are provided in the table 1. Computational expansion, the automated formal verification with the TLC model checker. This table contains 8 columns. First column represents the number of software threads that have been utilized during the experimentation. The second one represents the estimation function showing the number of milliseconds that have been spent to conduct the TLC-based model checking using the BFS implementation. The third column, alpha BFS, is the index representing the speed up from multi-threading when the BFS implementation of the TLC method takes place. The fourth column represents the total number of transition system states that have been generated during BFS-based formal verification. The fifth column represents the number of milliseconds that have been spent to verify the formal specification for the diagram depicted in the figure 1 using the DFS-based implementation of the TLC method. We can see that these expenses are significantly lower comparing to the BFS based one. So in this particular case, the DFS implementation of the TLC model checker is significantly more preferable comparing to the BFS alternative. In the sixth column, we can see the speed up from implementing the multi-threaded when using the DFS implementation of the TLC model checker. We can see that we have faced here the negative speed up. In the seventh column, we can see the average number of states generated during the DFS-based model checking. We can see here that these special expenses are significantly bigger comparing to the BFS-based ones. And the last column, CDFS, represents the index of the growth of these special expenses depending on the number of software threads utilized. You can see that moving from 1 to 8 threads, our special expenses when the DFS implementation of the TLC method takes place increased almost 2 times. Thus, in the table 1, it can be seen that the DFS implementation of the TLC method has appeared to be significantly more effective in terms of related computational expenses when comparing to the default BFS alternative, from about 1.902 times for thread number equals 1 to about 1.675 times for thread number equals 8. Thus, we can see that in this particular scenario, the DFS implementation of the TLC method is significantly more preferable, and to foster the named problem of decrease the effect from the exponential growth of transition system state space number, it's recommended to use the DFS implementation of the TLC. Experiments and results. In attempt to estimate the growth of the DFS-related special expenses from the number of software threads utilized, an approximation task has been resolved on the basis of the TN thread number parameters and the CDFS indexes. The results are depicted in the figure figure 2. As an outcome, the following estimation function has been obtained. Expression 1. The conclusions. Thus, broadly used TLC model checker has been investigated in given paper on the basis of the case-driven scenario taking place in modern energy domain. A role model describing the European identification codes registry update process has been addressed as a design artifact. The consistency of corresponding program algorithmic constituent has been proven with the named method applied. Obtained results have led us to a conclusion that the DFS implementation of the TLC method significantly depend on both the number of state variables taking place in formal specification and the architectural plane of the latter. At the same time, in general, on the basis of the case study conducted, the DFS implementation has appeared to be about 1.675 to 1.902 times more efficient in terms of their related time cost when compared to the default BFS implementation of the TLC. Thus, in this particular scenario, the DFS implementation of the TLC method is recommended to be used to foster the decrease of the negative effect from the exponential growth of the number of transition system state space. On the contrary, when addressing the spatial aspects, the number of transition system states generated, the DFS implementation has appeared to be significantly worse comparing to the BFS alternative, from about 12.482 to about 24.434 times. Thank you for your attention.